Welcome to Science Snippets Fun Facts and Trivia. Today, we bring you, can we build a perpetual motion machine? The challenge to energy conservation. Chapter 1. The Perpetual Motion Dream. Section 1. What is a perpetual motion machine? Imagine a machine that runs forever without needing any fuel or external energy. A device that defies the limits of physics, providing limitless energy and solving the world's power crisis. This is the dream of a perpetual motion machine, a concept that has fascinated inventors and scientists for centuries. But what exactly is a perpetual motion machine? In simple terms, it is a hypothetical device that can operate indefinitely without any external energy input. It would generate continuous motion and, in some cases, even produce excess energy. If such a machine were possible, it would revolutionize every aspect of human civilization, ending our dependence on fossil fuels, eliminating energy shortages, and drastically transforming industries worldwide. To understand why a perpetual motion machine is so intriguing, we need to break it down into different types. Scientists generally classify them into three categories. 1. Perpetual motion machines of the first kind. These machines claim to create energy out of nothing, directly, violating the first law of thermodynamics, which states that energy cannot be created or destroyed, only transformed. If such a device worked, it would mean we could extract infinite energy from nowhere. An idea that contradicts everything we know about physics. 2. Perpetual motion machines of the second kind. These machines attempt to produce work by extracting energy from their surroundings, usually in the form of heat, and converting it into useful energy with 100% efficiency. This contradicts the second law of thermodynamics, which states that energy transformations always result in some loss, usually as waste heat. No real system can be perfectly efficient, because entropy, or disorder, always increases. 3. Perpetual motion machines of the third kind. These are machines that claim to keep moving forever, without any energy loss due to friction or air resistance. While this might sound possible in a vacuum, in the real world, all motion experiences resistance, and eventually slows down unless energy is continuously supplied. Despite the scientific impossibility, the idea of perpetual motion has captivated humanity for centuries. The promise of limitless energy is simply too tempting to ignore. Throughout history, inventors and thinkers have proposed countless designs, hoping to find a loophole in physics. One of the earliest recorded attempts was made by Villard de Huncourt, a 13th-century French architect, who sketched a design featuring an overbalanced wheel. The idea was that the wheel's own weight distribution would keep it turning indefinitely. Similar designs appeared throughout the Renaissance, as thinkers like Leonardo da Vinci examined the concept, though he was quick to dismiss it as impossible. Even today, some inventors refuse to give up on the dream, claiming to have built working perpetual motion machines. Many of these designs involve magnets, clever mechanical tricks, or hidden power sources, but none have ever passed rigorous scientific testing. So, why do people keep trying? The answer lies in the powerful allure of infinite energy. If such a machine were possible, it would challenge our fundamental understanding of physics and unlock a new era of scientific discovery. But as we will explore in the next sections, the laws of thermodynamics stand in the way, seemingly making perpetual motion a dream that can never be realized. But is that truly the case? Or is there something science has yet to discover? Section 2. Why scientists and inventors keep trying. Despite overwhelming scientific evidence against perpetual motion, inventors and scientists have never stopped searching for a way to make it work. But why? What drives people to challenge the fundamental laws of physics, even when history is filled with failed attempts? The answer lies in three key factors: curiosity, the promise of free energy, and the hope of breaking scientific barriers. First, human curiosity knows no bounds. Since ancient times, people have sought ways to harness unlimited energy. The idea of a machine that runs forever without input is incredibly attractive because it challenges our understanding of the universe. Some believe that current physics might be incomplete, and that a yet-to-be-discovered principle could make perpetual motion possible. This mindset fuels countless new experiments, even when the odds are against success. Second, the promise of free energy is simply too tempting. If perpetual motion were possible, it would revolutionize society. Imagine a world where electricity is limitless and free, where no one needs fossil fuels, batteries, or power plants. Entire industries would be transformed, and economic disparities caused by energy scarcity would vanish. The impact on technology, space exploration, and everyday life would be enormous. This vision of a utopian future keeps many inventors motivated, despite scientific skepticism. Finally, history has shown that scientific impossibilities can sometimes be overturned. Throughout history, ideas once thought impossible, like heavier-than-air flight, nuclear energy, and quantum mechanics, eventually became reality. Some inventors believe that the laws of thermodynamics might not be absolute, or that unknown physical phenomena could be harnessed in ways we don't yet understand. Even mainstream scientists acknowledge that while perpetual motion is impossible under current physics, our understanding of the universe is always evolving. This relentless pursuit has led to thousands of perpetual motion designs. Some rely on magnetic forces, cleverly arranged weights, or innovative materials. Others incorporate electrical or quantum effects, in the hopes of bypassing energy loss. While none have succeeded under rigorous scientific scrutiny, they continue to inspire new generations of thinkers and experimenters. So, will someone ever build a working perpetual motion machine? Most scientists say no, but as long as human curiosity and ambition exist, people will keep searching, pushing the limits of what we believe is possible. Section 3. The most famous historical attempts. Throughout history, many inventors have tried to build a perpetual motion machine, each believing they had found a way to defy physics. While all ultimately failed, their attempts reveal the human drive for innovation and the deep desire to unlock unlimited energy. Let's explore some of the most famous efforts. One of the earliest recorded designs came from Villard de Huncourt, a 13th-century French architect. He sketched a wheel with weights attached to its spokes, believing that the shifting weight distribution would keep it spinning forever. This concept, called the overbalanced wheel, was one of the most popular perpetual motion designs for centuries. However, scientists later proved that the forces acting on the wheel would always balance out, eventually bringing it to a stop. In the 17th century, Robert Fludd, an English physician and mystic, proposed a self-sustaining water wheel. His design used a water pump to recycle the water that turned the wheel, creating continuous motion. While it looked promising on paper, it ignored the energy loss due to friction and inefficiencies in the pumping system. No version of this machine ever worked. During the Renaissance, even Leonardo da Vinci studied perpetual motion. While others tried to build machines, da Vinci disproved their designs, showing mathematically why they couldn't work. His notebooks contain sketches of overbalanced wheels, with notes explaining how they would always slow down and stop. In the 18th century, Johann Bessler, also known as Orpheus, became famous for claiming he had built a working perpetual motion machine. He demonstrated his invention to multiple witnesses, who confirmed that the wheel spun for long periods without an apparent energy source. However, Bessler refused to let scientists examine the internal mechanism. When he died, the secret died with him. Many believe he used hidden mechanisms, or external forces, to create the illusion of perpetual motion. Moving into the 19th century, Charles Redheffer, an American inventor, built a perpetual motion machine that attracted public attention. He even convinced investors to fund his work. However, skeptics eventually discovered that his device was secretly powered by a hidden human operator, turning a crank in the next room. His fraud was exposed, but not before he had made a considerable profit. Even in the 20th and 21st centuries, people continue to claim they have discovered perpetual motion. Many designs involve magnets, electrical systems, or advanced materials. Some inventors believe that modern physics may hold undiscovered loopholes that could make perpetual motion possible. However, no design has ever passed independent scientific testing. These historical attempts highlight the persistence of human ingenuity, even when facing the impossible. Despite repeated failures, the search for a limitless energy source continues. But as we will see in the next chapter, the fundamental laws of physics present a major obstacle to this dream. Chapter 2: The Physics That Says Impossible. Section 1: The Laws of Thermodynamics Explained. If perpetual motion were possible, it would defy one of the most fundamental principles of physics, the laws of thermodynamics. These laws describe how energy behaves in the universe, and they are the reason why no machine has ever been able to run indefinitely without an energy source. Let's break down the three main laws of thermodynamics and see why they make perpetual motion impossible. The first law of thermodynamics: the conservation of energy. This law states that energy cannot be created or destroyed, only transformed from one form to another. In other words, you can't get something from nothing. A perpetual motion machine of the first kind, which claims to create energy out of nothing, would directly violate this principle. For example, when you burn fuel in a car engine, the chemical energy is converted into heat and motion, but the total energy remains the same. It's just changing forms. If a machine were to generate more energy than it started with, it would mean energy is appearing out of nowhere, breaking this fundamental law of nature. The second law of thermodynamics: entropy always increases. Even if a machine doesn't create energy from nothing, could it at least keep running forever by perfectly recycling its energy? The second law of thermodynamics says no. This law states that every energy transfer increases entropy, which is a measure of disorder. Whenever energy is converted from one form to another, some of it is always lost as heat. This is why no real-world machine can be 100% efficient. For example, think of a spinning top. As it turns, friction between the top and the air converts some of its kinetic energy into heat, slowing it down until it eventually stops. This happens with all machines. Friction, air resistance, and other inefficiencies always lead to energy loss. A perpetual motion machine of the second kind, which claims to run indefinitely without losing energy, would have to somehow bypass entropy, something no machine has ever done. The third law of thermodynamics: absolute zero is unreachable. While not as directly related to perpetual motion, the third law states that As a system approaches absolute zero minus 273.15 degrees Celsius, its entropy approaches a minimum, but absolute zero can never be reached. Some inventors have theorized that a machine operating in an extremely cold environment might reduce energy loss enough to achieve perpetual motion. However, because absolute zero is physically impossible to reach, there will always be some energy loss in any real-world system. Why these laws are considered unbreakable? The laws of thermodynamics are not just theories. They have been confirmed by countless experiments and are fundamental to modern science. They govern everything from how engines work to how stars burn fuel. For a perpetual motion machine to exist, one or more of these laws would have to be proven wrong or incomplete. So far, no experiment has ever shown a violation of these principles. But does that mean the search is hopeless? Or could there be hidden loopholes within physics that we haven't discovered yet? In the next section, we'll explore another major obstacle to perpetual motion: friction, heat, and the inevitable loss of energy in real-world systems. Section 2. Friction, heat, and energy loss. Even if a machine could theoretically run forever without needing new energy, real-world forces always get in the way. The biggest obstacles? Friction, heat, and energy loss. These unavoidable factors ensure that every moving system eventually slows down and stops. Friction, the hidden energy thief. Friction occurs whenever two surfaces rub against each other, converting some of their motion into heat. No matter how smooth or well lubricated a machine is, there is always some friction. For example, consider a spinning wheel. As it turns, its axle rubs against its support, generating heat and losing energy. Even in space, where there is no air resistance, internal friction within the machine itself would still cause energy loss over time. Heat, the unstoppable drain on energy. Every mechanical system generates heat, whether from friction, air resistance, or electrical resistance. This heat disperses into the environment, making it impossible to recover all the original energy. A good example is an engine. Even with advanced cooling systems, engines waste a huge percentage of their energy as heat rather than useful motion. This is why no machine is ever 100% efficient. Air resistance, the invisible brake. Even if friction were somehow eliminated, air resistance would still be a problem. As an object moves, it collides with air molecules, transferring energy to them and slowing down. This is why a fan blade stops spinning once power is cut. It transfers its energy to the surrounding air. Some perpetual motion designs try to remove air resistance by operating in a vacuum. While this can reduce energy loss, it doesn't eliminate internal friction or heat generation within the machine itself. The inevitable loss of energy. Because of these factors, every real-world machine slowly loses energy and eventually stops unless new energy is added. This is why perpetual motion machines of the third kind, which claim to move indefinitely without energy loss, are just as impossible as the other types. So, can we ever overcome these obstacles? Or is there something fundamental we're missing? In the next section, we'll explore why, despite all these challenges, some still believe that a loophole in physics might make perpetual motion possible. Section 3. Why no machine has ever succeeded. For centuries, inventors have pursued the dream of perpetual motion, but every attempt has ultimately failed. Why? The answer lies in the fundamental laws of physics and the inescapable realities of energy loss. No matter how clever the design, every machine ever built has run into the same problems, violating the laws of thermodynamics. As we discussed earlier, perpetual motion machines would need to create energy from nothing, violating the first law of thermodynamics, or operate with perfect efficiency, violating the second law of thermodynamics. Every verified scientific experiment has confirmed that these laws hold true. In all observed cases, some inventors argue that they have found exceptions, but when tested under controlled conditions, their machines always fail. Many so-called successful devices have turned out to rely on hidden energy sources, measurement errors, or outright fraud. Energy loss is inevitable, even in a vacuum, where there is no air resistance. Machines still experience internal friction between their moving parts, bearings, gears, and even atomic vibrations, cause tiny amounts of energy to be lost as heat. Over time, this energy loss accumulates, causing the system to slow down and stop. For example, even the best engineered flywheels, which store rotational energy, slow down after a while, no matter how well they are designed. The same applies to superconductors, which can maintain electric currents with almost no resistance, but still require external cooling systems to prevent energy loss. The role of scientific scrutiny. Many inventors throughout history have claimed to have built working perpetual motion machines, but when their devices were carefully examined, they never held up to scrutiny. Some inventors were sincere but made errors in their calculations. Others intentionally misled investors for profit. One famous example is Johann Bessler Orffyreus, who in the 18th century claimed to have built a self-moving wheel. While witnesses reported seeing the wheel spin for long periods, Bessler refused to let anyone examine its internal mechanism. When skeptics demanded a thorough test, he destroyed his machine, ensuring that his secret was never revealed. Most historians believe it was a clever hoax. Why do people still try? Despite these failures, the hope of unlimited energy continues to inspire new attempts. Some believe that modern technology, such as quantum mechanics or AI-driven optimizations, could reveal a loophole that earlier scientists missed. However, as of today, no perpetual motion machine has ever worked under scientific testing. Every successful machine ever built still requires some form of energy input, no matter how small. So, is the dream of perpetual motion truly dead? Or is there a possibility that new discoveries could change our understanding of physics? In the next chapter, we'll explore modern theories that challenge our current scientific knowledge and examine whether perpetual motion might someday become a reality. Chapter 3. Theories that challenge the limits. Section 1. Quantum mechanics and energy extraction. While classical physics firmly rejects the idea of perpetual motion, quantum mechanics, the science of the very small, introduces strange and counterintuitive possibilities. Could quantum effects offer a loophole to extract unlimited energy? Some scientists believe there might be ways to harness energy from the very fabric of reality itself. The mystery of zero-point energy. One of the most intriguing ideas in quantum physics is zero-point energy. Even in the coldest, emptiest vacuum, where no particles seem to exist, quantum fields still fluctuate. These fluctuations, known as vacuum energy, suggest that space itself contains a hidden reservoir of energy. Physicist Richard Feynman once calculated that the energy density of empty space could be immense, possibly enough to boil all the oceans on Earth. But despite this enormous theoretical energy, no practical method has been found to extract it. The problem is that zero-point energy exists in a balanced state, meaning we can't tap into it without violating the laws of physics. as we currently understand them. The Casimir effect, a glimpse of free energy? In 1948, physicist Hendrik Casimir discovered that two uncharged metal plates, placed very close together in a vacuum, would experience a small attractive force due to quantum fluctuations. This is known as the Casimir effect. Some have speculated that this force could be harnessed to generate energy. However, while the Casimir effect demonstrates the reality of vacuum energy, it doesn't provide a way to extract usable power. The force is extremely weak, and so far, no one has developed a way to turn it into a self-sustaining energy source. Quantum tunneling and energy extraction. Another strange quantum phenomenon is quantum tunneling, where particles can pass through energy barriers they shouldn't be able to overcome. Some theorists have suggested that quantum tunneling could allow us to access new energy sources, but so far, no practical application has been found that defies thermodynamics. Can quantum mechanics unlock perpetual motion? While quantum physics challenges many classical ideas, it still obeys fundamental conservation laws. No experiment has ever shown a violation of energy conservation at a macroscopic scale. However, research into quantum energy remains ongoing. Some physicists speculate that future discoveries might reveal a way to manipulate vacuum energy or other quantum effects in ways we don't yet understand. If that happens, we could be on the verge of an energy revolution. But are there other exotic possibilities beyond quantum mechanics? In the next section, we'll explore the strange concept of negative energy and its potential role in defying traditional physics. Section 2. Negative energy and exotic theories. While conventional physics tells us that perpetual motion is impossible, some exotic theories suggest that under the right conditions, energy could flow in unexpected ways. One of the most intriguing possibilities is negative energy, a concept that challenges our understanding of how energy works in the universe. What is negative energy? In classical physics, energy is always a positive quantity. You need energy to move, heat an object, or power a machine. But in certain theoretical frameworks, such as quantum field theory and general relativity, negative energy appears as a mathematical possibility. Negative energy isn't just about having less than zero energy. It refers to exotic conditions where energy behaves in counterintuitive ways. Some physicists believe that if we could generate and control negative energy, it might be possible to create systems that operate beyond the limits of classical thermodynamics. Exotic matter and wormholes. One place where negative energy becomes crucial is in wormhole physics. According to Einstein's theory of general relativity, a traversable wormhole, a shortcut through spacetime, would require negative energy to remain stable. Without it, the wormhole would collapse instantly. If negative energy can stabilize a wormhole, could it also be used to reduce friction or prevent energy loss in machines? Some have speculated that manipulating negative energy could lead to new forms of energy generation. However, so far, negative energy remains purely theoretical, with no proven method of harnessing it for practical use. Hawking radiation and energy extraction. Stephen Hawking proposed that black holes slowly evaporate due to a quantum effect known as Hawking radiation. This process involves the creation of particle-antiparticle pairs at the event horizon, where one particle falls into the black hole while the other escapes. The escaping particle carries away energy, effectively stealing it from the black hole. Some theorists have wondered whether a similar process could be used to extract energy from spacetime itself. However, no practical method for doing so has been discovered. Could negative energy power a perpetual motion machine? While negative energy is a fascinating concept, no experiment has ever demonstrated a way to create or use it in a controlled manner. Even if it could be generated, it might not be usable for mechanical work. Just as dark energy appears to drive the universe's expansion, but can't be harnessed like electricity. Still, the fact that negative energy appears in serious physics, research suggests that our understanding of energy is not yet complete. Could future discoveries reveal a hidden loophole that allows energy to be manipulated in ways we never imagined? In the next section, we'll explore another mysterious quantum phenomenon, the Casimir effect, and whether it could hold the key to unlocking free energy. Section 3. The Casimir effect and zero-point energy. In the strange world of quantum mechanics, even empty space is not truly empty. Instead, it is filled with quantum fluctuations, tiny bursts of energy that appear and disappear constantly. One of the most intriguing consequences of this phenomenon is the Casimir effect, which seems to suggest that energy can be extracted from the vacuum itself. Could this be the key to perpetual motion? The Casimir effect proof of vacuum energy. In 1948, Dutch physicist Hendrik Casimir predicted a bizarre quantum effect. If two uncharged, parallel metal plates are placed extremely close together in a vacuum, they will experience a small but measurable force pulling them toward each other. This happens because quantum fluctuations in the surrounding space create more virtual particles outside the plates than between them, causing a pressure difference. This was later confirmed experimentally, proving that quantum vacuum energy is real. Some theorists speculated that if we could somehow exploit this force, it might be possible to generate energy from the vacuum itself. Can the Casimir effect be used for free energy? At first glance, the Casimir effect seems like a potential loophole. In the laws of thermodynamics, if we could harness vacuum energy, it might allow for a self-sustaining energy source, breaking the limitations that prevent perpetual motion. However, there are major obstacles. The force is incredibly weak. In most experiments, the Casimir force is only detectable at distances of a few nanometers, making it difficult to scale up for practical energy production. It requires external energy to reset. Moving the plates apart after they attract each other requires an input of energy, making it impossible to create a net energy gain. It does not violate thermodynamics. While quantum fluctuations exist, they do not allow for usable energy extraction in a way that would break known physical laws. Zero-point energy, a vast but inaccessible power source. Zero-point energy refers to the lowest possible energy state of a quantum system. Even at absolute zero, atoms still retain some motion due to quantum uncertainty. Some have suggested that this vast but hidden energy reservoir might be tapped for limitless energy. Physicist Richard Feynman once estimated that the vacuum energy contained in a single cubic centimeter of space could be enough to power the entire planet. However, zero-point energy exists in a perfectly balanced state, meaning there is no known way to extract useful work from it without violating conservation laws. The dream versus reality. While the Casimir effect and zero-point energy provide compelling evidence that quantum fluctuations are real, no experiment has ever demonstrated a way to use them for perpetual motion or free energy. However, research into quantum energy remains ongoing. If future breakthroughs reveal ways to manipulate vacuum energy more effectively, we may one day discover a method to harness it. But for now, perpetual motion remains an unachieved dream, one that quantum mechanics has yet to fulfill. In the next chapter, we'll examine modern claims of perpetual motion and whether any of them hold up under scientific scrutiny. Chapter 4: Modern Claims and Scientific Reality. Section 1: Overunity devices, do they work? Despite the scientific consensus that perpetual motion is impossible, there are still inventors and researchers who claim to have built machines that produce more energy than they consume. These so-called overunity devices supposedly achieve an efficiency greater than 100%, meaning they generate excess energy without an external source. If true, they would revolutionize the world. But do any of them actually work? What is an overunity device? The term overunity refers to any system that claims to produce more energy than it receives. Unlike traditional perpetual motion machines, which attempt to run indefinitely without energy input, overunity devices often claim to extract energy from unknown or poorly understood sources, such as the quantum vacuum, electromagnetic fields, or even gravity itself. Some of the most famous overunity concepts include magnetic motors that supposedly sustain motion indefinitely, using repelling magnetic forces, electromagnetic generators that claim to amplify energy input beyond normal efficiency limits, gravity-based machines that claim to generate free energy by exploiting gravitational forces. Famous overunity claims. Over the years, numerous inventors have announced the discovery of a working overunity device. Some of the most well-known examples include John Bedini's self-charging battery system, which allegedly harnessed energy from the environment; Stearns' Orbo device, an Irish company's claimed breakthrough in free energy, which failed public demonstrations; the Purindev magnetic motor, which was promoted as a working perpetual motion machine, but was never independently verified. Each of these devices attracted significant attention, with some inventors even securing financial backing. However, none have passed rigorous scientific testing, and many were later exposed as miscalculations or outright frauds. Why do overunity devices always fail? The reason why overunity machines don't work is simple. They still cannot bypass the laws of thermodynamics. Every working energy system must account for energy input and output, even if a machine appears to generate extra energy. Detailed testing always reveals hidden energy sources or measurement errors. Friction and resistance, mechanical and electrical systems always experience some energy loss due to heat, friction, or inefficiencies. Scientific validation: no overunity device has ever been successfully demonstrated under controlled, repeatable conditions. The reality behind overunity claims: while many inventors genuinely believe in their discoveries, others have been caught intentionally misleading the public. Some overunity scams have resulted in millions of dollars lost to fraudulent investment schemes. Governments and independent researchers regularly test such claims, but no working device has ever been confirmed. So, is it all just a fantasy? Or could new breakthroughs, like artificial intelligence or advanced physics, reveal something we've missed? In the next section, we'll explore how modern technology is shaping the search for new energy sources. Section 2: AI and New Energy Discoveries. Artificial intelligence (AI) is transforming almost every field of science, and energy research is no exception. While perpetual motion remains impossible according to current physics, AI is helping scientists explore new ways to improve energy efficiency, optimize renewable sources, and even investigate unconventional energy phenomena. Could AI bring us closer to a breakthrough that challenges our understanding of energy? How AI is revolutionizing energy research. AI is particularly powerful in fields that require analyzing massive datasets and identifying complex patterns. In the search for better energy solutions, AI is being used to optimize energy systems. AI-driven algorithms can enhance the efficiency of power grids, reducing energy loss. Improve battery technology. Machine learning models predict new materials for high-efficiency, long-lasting batteries. Explore alternative energy sources. AI is accelerating research into fusion power and other advanced energy technologies. Although AI does not create energy, it helps scientists find better ways to use and store it, a critical step toward achieving more sustainable energy systems. AI and the search for new physics. One of the most exciting areas where AI could have an impact is fundamental physics. Some researchers are using AI to analyze quantum mechanics, vacuum fluctuations, and exotic energy fields, hoping to uncover previously unknown phenomena. For example, AI has been applied to quantum field simulations, helping physicists explore complex interactions that might reveal new ways to manipulate energy. While this doesn't mean perpetual motion is possible, it does suggest that our understanding of energy is still evolving. Could AI help find a loophole in thermodynamics? Some futurists speculate that AI could help identify undiscovered principles in physics that might allow for more efficient energy use, or even reveal new sources of energy. While this remains speculative, history has shown that major breakthroughs often come from unexpected places. For now, AI is not rewriting the laws of physics, but it is playing a crucial role in advancing next-generation energy technologies. Whether that leads to a revolution in our understanding of energy remains to be seen. In the next section, we'll examine how scientists approach claims of free energy, and why skepticism remains an essential part of scientific progress. Section 3. Scientific skepticism and debunking. Throughout history, claims of perpetual motion and free energy have attracted attention, excitement, and sometimes even financial investment. But every time such a claim is put to the test, it fails to meet scientific scrutiny. Why does skepticism remain so strong? And how do scientists separate real discoveries from pseudoscience? Why scientific skepticism is necessary? Science is built on evidence, experimentation, and repeatability. If someone claims to have created an energy-generating machine that defies known physics, the scientific method requires that the results must be independently verified. Can other researchers reproduce the same results under controlled conditions? All possible explanations must be tested. Could the observed effect be caused by hidden energy sources, measurement errors, or external interference? The findings must not contradict well-established physical laws, unless new evidence is strong enough to challenge those laws. Extraordinary claims require extraordinary evidence. No perpetual motion or overunity device has ever passed these tests. Common reasons why free energy claims fail. Many perpetual motion and overunity devices are eventually debunked due to misinterpretation of results. Inventors sometimes mistake energy transfer for energy creation. Hidden power sources. Some devices unknowingly draw energy from external sources, like batteries or environmental factors. Fraud. Unfortunately, some individuals have deliberately faked results to attract investors or publicity. One famous case is Stearns Orbo, a device that was claimed to generate free energy through magnetism. In public demonstrations, the machine failed to operate as promised, and no scientific validation was ever provided. The role of peer review and testing. Whenever a bold new energy claim is made, Scientists and engineers conduct rigorous tests to check its validity. Institutions like MIT, NASA, and independent physics labs have examined various free energy devices over the years, but none have proven to work. Even when testing unconventional energy sources like zero-point energy or vacuum fluctuations, researchers have not found a way to extract useful work without violating the laws of thermodynamics. The importance of open-minded skepticism. Skepticism does not mean rejecting new ideas outright. It means demanding strong evidence before accepting extraordinary claims. While perpetual motion has been debunked time and time again, science continues to explore new energy technologies in responsible, evidence-based ways. In the next chapter, we'll shift our focus to the future of energy science, examining whether emerging technologies like fusion power and advanced renewables could bring us closer to an era of limitless energy. Chapter 5: The Future of Energy Science. Section 1: Advanced renewable energy versus perpetual motion. While perpetual motion machines remain impossible, modern energy technologies are getting closer to maximizing efficiency and sustainability. Advances in renewable energy and nuclear fusion promise an era of abundant power, though they still require external energy sources. How do these real-world innovations compare to the fantasy of perpetual motion? The core difference: science versus fiction. Perpetual motion machines claim to generate energy endlessly without input, violating thermodynamics. In contrast, advanced renewable energy systems extract energy from natural, sustainable sources while staying within the laws of physics. For example, solar power converts sunlight into electricity, with modern panels reaching efficiencies of over 40%. Wind energy harnesses atmospheric motion, with turbine designs improving to generate more power from weaker winds. Geothermal energy taps into Earth's internal heat, providing a continuous and stable power source. Hydroelectric power captures gravitational energy from flowing water, remaining one of the most reliable renewable sources. These technologies do not defy physics, but work by capturing energy already present in nature. Fusion power, the closest thing to unlimited energy? One of the most exciting breakthroughs in energy research is nuclear fusion, the process that powers stars. Unlike nuclear fission, which splits atoms, fusion combines hydrogen atoms, releasing immense energy with minimal waste. Scientists are developing tokamak reactors like those in the ITER project, aiming to sustain a controlled fusion reaction. If successful, fusion could provide near limitless energy, but it still requires fuel and extreme conditions. Unlike the fantasy of perpetual motion, could future advances feel like perpetual motion? While a true perpetual motion machine is impossible, future energy breakthroughs could make energy seem limitless. Next-generation batteries may store power more efficiently, reducing waste. Superconductors could eliminate energy loss in electrical grids. AI-driven energy management may optimize production and consumption to nearly eliminate inefficiencies. We may never break the laws of physics, but we might come close to an era where energy is so abundant, efficient, and cheap that it feels like perpetual motion. In the next section, we'll explore whether future scientific discoveries could ever allow us to overcome the known limits of physics. Section 2: Could we ever overcome physics? The laws of physics, particularly thermodynamics, seem absolute, preventing perpetual motion from becoming reality. However, history has shown that scientific breakthroughs can challenge long-held beliefs. Could we ever discover new principles that redefine our understanding of energy? Or will these fundamental laws always remain unbreakable? When science has challenged the impossible throughout history, ideas once thought impossible have become reality. Flight, once dismissed as unachievable, now essential to transportation. Quantum mechanics. Classical physics couldn't explain atomic behavior until quantum theory emerged. Nuclear energy. The idea of extracting power from atoms seemed absurd before fission and fusion were discovered. These breakthroughs didn't break physics, they expanded our understanding. Could something similar happen with energy? Where could a breakthrough come from? Some areas of modern physics remain mysterious and could one day provide new insights into energy. Dark energy and dark matter. These make up most of the universe, yet we barely understand them. If we could harness dark energy, it could redefine energy conservation. Quantum vacuum. Energy fluctuations in empty space suggest untapped energy potential, but no method exists to extract it efficiently. New fundamental forces. If undiscovered forces exist beyond gravity and electromagnetism, they might offer alternative ways to generate or manipulate energy. Are there limits to scientific advancement? Even if new physics is discovered, violating thermodynamics is a different challenge. Science progresses by refining knowledge, but completely overturning foundational laws is extremely rare. For example, Einstein's theory of relativity didn't invalidate Newton's laws. It showed they were a special case in a broader framework. Similarly, any future energy breakthroughs would likely work within thermodynamic principles, rather than defying them. Could energy ever feel unlimited? While true perpetual motion is impossible, future advancements may create an energy-rich world. Fusion power. If mastered, fusion could provide near-infinite clean energy. Superconductors. Eliminating energy loss in power. Grids could maximize efficiency. AI-optimized energy systems. Smarter management of power distribution could minimize waste and improve sustainability. Though physics imposes limits, future discoveries may push the boundaries of what we consider possible. A world where energy is so abundant and efficient that it feels limitless may not be as far away as we think. In the next section, we'll explore the ethical and practical consequences of achieving near-limitless energy. Would it bring prosperity or introduce new risks and challenges? Section 3. The ethical and practical implications. If humanity were to unlock a nearly limitless energy source, it would be one of the greatest discoveries in history. The elimination of energy scarcity could lead to technological revolutions, economic growth, and environmental benefits. However, such an advancement could also create unintended risks, ethical dilemmas, and geopolitical conflicts. Would infinite energy bring a utopia or destabilize the world? The potential benefits of unlimited energy. A world with abundant, nearly free energy could transform society in profound ways, ending energy poverty. Billions of people without access to reliable power could benefit from unlimited energy, improving living standards worldwide. End of fossil fuel dependence. Coal, oil, and gas industries would collapse, reducing carbon emissions and slowing climate change. Scientific and technological breakthroughs. Advanced AI, space exploration, and medical research could accelerate without energy constraints. Economic expansion. Manufacturing, transportation, and digital services would become significantly cheaper, fueling rapid global development. With energy no longer a limiting factor, humanity could pursue grand projects, such as terraforming Mars, deep space travel, and large-scale climate engineering. The risks and ethical challenges. Despite its promise, unlimited energy could introduce new dangers. Geopolitical instability: nations that rely on fossil fuel exports could experience economic collapse, leading to political unrest and power struggles. Environmental overuse: cheap energy might encourage reckless industrial expansion, leading to excessive resource consumption and habitat destruction. Energy as a weapon: access to vast amounts of energy could enable the development of superweapons, or increase the risk of warfare. Unequal distribution: if only a few corporations or nations control the technology, economic inequality could worsen instead of improving. Would limitless energy lead to a utopia or dystopia? History has shown that technological progress alone does not guarantee a better world. It depends on how power is managed and distributed. If handled responsibly, nearly unlimited energy could bring prosperity and peace. However, if misused, it could lead to new conflicts, environmental disasters, and economic disruptions. In the next chapter, we'll explore a thought experiment: what if perpetual motion were truly possible? How would it reshape the world? Chapter 6: The impact of free energy if possible. Section 1: A world without energy scarcity. Imagine a world where energy is truly unlimited, where electricity flows freely, transportation never requires refueling, and industries operate without energy costs. If perpetual motion or an equivalent breakthrough were achieved, it would reshape civilization on a scale never seen before. But what would such a world actually look like? A revolution in daily life. For individuals, unlimited energy would make basic needs far more accessible. Electricity would be free, eliminating power bills forever. Clean water could be produced anywhere, using energy-intensive desalination. Food production could expand dramatically, with vertical farms and lab-grown meat operating at full efficiency. Transportation would be transformed, with cars, trains, and planes operating without fuel costs. With energy freely available, the cost of living could drop significantly, leading to a major increase in the global standard of living. Industries without limits. The effects on industries would be even more dramatic. Factories could run 24/7 at no extra cost, making goods cheaper and more abundant. AI and computing would advance exponentially as unlimited power removes technological bottlenecks. Space exploration would enter a new era, with limitless energy for propulsion, life support, and asteroid mining. Large-scale climate engineering could become a reality, possibly controlling weather patterns and reversing environmental damage. However, the disappearance of energy costs would destabilize global markets. The oil, coal, and gas industries, worth trillions of dollars, would collapse, leading to economic upheaval and mass unemployment in traditional energy sectors. Would society become a utopia? At first glance, a world without energy scarcity seems like paradise. However, history has shown that new technologies often bring unintended consequences. Resource overconsumption with no energy limits. Industries might exploit Earth's resources unsustainably. Economic disruptions. Energy exporting countries could face collapse, leading to global instability. Power struggles. If a single corporation or government controlled this energy source, it could lead to monopolies or conflicts over access. A world with unlimited energy could bring unprecedented prosperity, but it would also require new systems of governance and regulation to prevent new crises. In the next section, we'll explore how this energy revolution could reshape economies and the environment on a global scale. Section 2: Economic and environmental transformations. A world with unlimited energy would trigger profound economic and environmental changes. While it could drive prosperity and sustainability, It could also create instability and unforeseen risks. How would industries, global economies, and the environment react to a sudden energy revolution? The economic disruption, a collapse or a boom? The immediate effect of unlimited energy would be the collapse of traditional energy industries. Oil, coal, and gas industries would disappear, wiping out trillions of dollars in global markets. Energy exporting countries would lose their main source of income, leading to political and economic crises. Power companies and utility providers would become obsolete, forcing millions of workers to transition to new industries. However, new industries would emerge to take advantage of limitless energy. Manufacturing costs would plummet, making goods cheaper and more abundant. AI, robotics, and automation would accelerate, revolutionizing industries that rely on high-energy computing. Space exploration and asteroid mining could become profitable, creating entirely new economic sectors. If managed wisely, this shift could lead to an economic boom. However, if left uncontrolled, it could create mass unemployment and geopolitical instability. Environmental impacts, a green future or a new crisis. On the surface, unlimited energy seems like an environmental dream. Fossil fuel emissions would disappear drastically, reducing climate change effects. Clean water would be abundant, as energy-intensive desalination becomes cheap. Deforestation and habitat destruction could be reversed, with artificial ecosystems powered by limitless energy. However, abundant energy could also lead to overconsumption of resources. Industries could extract materials at an unsustainable rate, leading to shortages and environmental degradation. Mass urban expansion could damage natural ecosystems, as unlimited power allows for massive new infrastructure projects. Geoengineering could be used recklessly, with unintended consequences for the planet's climate system. A delicate balance between growth and sustainability. Unlimited energy has the potential to create a cleaner, more advanced world, but only if properly regulated. Without careful planning, it could lead to economic chaos, resource depletion, and new environmental risks. In the next section, we'll explore a deeper question. Would a world with limitless energy truly be a utopia? Or could it bring new dangers that we haven't considered? Section 3. Would it be a utopia or a disaster? A world with unlimited energy sounds like a dream come true. No power shortages, no fossil fuel dependency, and endless opportunities for technological growth. But history has shown that major advancements often come with unexpected consequences. Could limitless energy truly lead to a utopia? Or would it create new dangers that we cannot yet foresee? The utopian vision, a world of infinite possibilities. If energy were no longer a limiting factor, the benefits would be staggering. Global poverty could be eradicated, as clean water, food, and shelter become universally accessible. Energy-intensive industries could provide resources at virtually no cost. Fossil fuel pollution would vanish, eliminating carbon emissions and halting climate change. Technological and medical progress would accelerate, as AI, quantum computing, and advanced healthcare operate without energy restrictions. Space exploration could advance rapidly, with energy no longer a barrier to deep space missions, colonization, and asteroid mining. This kind of progress could reshape society, shifting human focus away from survival and competition toward innovation, exploration, and creativity. The dystopian risks unforeseen consequences. Despite the potential benefits, unlimited energy could also bring about new and complex challenges. Uncontrolled resource consumption. With unlimited energy, industries might extract raw materials at unsustainable rates, leading to environmental destruction. Economic disruption. The collapse of the energy sector could cause mass unemployment and economic instability, particularly for nations reliant on energy exports. Geopolitical power shifts. If only a few entities control this energy source, wealth and power disparities could grow even larger, sparking new conflicts. Weaponization of infinite energy. Advanced weapons powered by limitless energy could escalate global warfare, making conflicts far more devastating. A world without energy scarcity does not mean a world without human greed, power struggles, or environmental concerns. Would humanity use unlimited energy wisely? The future of such a world would depend entirely on how society chooses to use this power. If managed responsibly, it could create an era of prosperity, peace, and sustainability. But if misused, it could lead to catastrophic overconsumption, inequality, and even existential threats. Technology alone does not determine the fate of civilization, human decisions do. In the next chapter, we'll ask an even deeper question: should we continue searching for the impossible? Or is perpetual motion a fantasy best left behind? Chapter 7: The Final Verdict. Section 1: Should we keep searching for the impossible? For centuries, humanity has been captivated by the dream of perpetual motion, an engine that runs forever, producing endless energy with no external input. Science tells us that such a machine is impossible, yet people continue searching for loopholes, hidden physics, and revolutionary discoveries. Should we keep chasing what seems to be an unattainable dream? Or is it time to accept the limits of nature? Why scientists say it's impossible? The laws of thermodynamics remain unbroken, no matter how many experiments are conducted. Perpetual motion machines always fail due to friction, energy loss, and the fundamental principle that energy cannot be created from nothing. Even quantum physics, which challenges many classical assumptions, has yet to provide a practical way to extract unlimited usable energy. Every claim of a working perpetual motion machine has either been debunked, exposed as a misunderstanding, or proven to rely on hidden energy sources. This has led mainstream science to conclude that continuing the search is a waste of time and resources. Why some believe we shouldn't give up. Despite these challenges, some argue that scientific progress is built on questioning the impossible. Many groundbreaking discoveries, electricity, flight, nuclear power, were once thought to be unattainable. Skeptics once dismissed heavier than air flight, yet today, we have supersonic jets and space travel. Furthermore, fields like quantum mechanics, dark energy research, and vacuum energy exploration suggest that our understanding of the universe is far from complete. If new physics is discovered, it might reveal unexpected ways to generate and harness energy beyond current scientific models. The real value of the search, even if perpetual motion is never achieved, the pursuit of it has led to important innovations. More efficient machines. Engineers striving for perfect efficiency have created better engines, motors, and energy storage systems. Renewable energy advancements. The desire for unlimited energy has driven research into solar, wind, and nuclear fusion technologies. Deeper understanding of physics investigating the impossible has led to breakthroughs in thermodynamics and quantum mechanics. So, should we keep searching? If the goal is a true perpetual motion machine, science suggests we are chasing a fantasy. But if the goal is to push the limits of human knowledge and discover new energy solutions, then the pursuit of the impossible may still lead to world-changing breakthroughs. In the next section, we'll explore what the future might reveal, Could the next great energy revolution be closer than we think? Section 2. What science might discover next. While perpetual motion remains impossible under current physics, scientific discovery is far from over. History has shown that breakthroughs often come from unexpected places, reshaping our understanding of energy and the universe. If we can't achieve infinite energy through perpetual motion, what other revolutionary discoveries might the future hold? 1. Quantum energy extraction. Quantum mechanics has already revealed bizarre effects like zero-point energy, a form of energy present even in a perfect vacuum. While current theories suggest that zero-point energy is not extractable in a usable way, some physicists believe there might be mechanisms we haven't yet discovered. If a method to harness it were found, it could provide a nearly limitless energy source without breaking thermodynamics. 2. Dark energy and exotic physics. Dark energy, which is responsible for the accelerating expansion of the universe, makes up about 68% of the cosmos. Yet we have no clear understanding of what it actually is. If future research uncovers how to manipulate dark energy, it could open the door to new methods of energy generation, perhaps even technologies that challenge our current understanding of physics. 3. Nuclear fusion advancements. Fusion energy, the process that powers the sun, has long been seen as the key to nearly unlimited clean power. Scientists are already making significant progress with fusion reactors like ITER and private sector projects, which aim to generate more energy than they consume. A breakthrough in sustained and efficient fusion would bring us as close as possible to an infinite energy source, while still obeying the laws of physics. 4. Superconductors and perfect efficiency. While perpetual motion is impossible, achieving near-perfect efficiency is not. Recent developments in room temperature superconductors suggest we may be able to build electrical systems with almost zero energy loss. If these materials can be scaled up, they could revolutionize energy transmission and storage, drastically reducing waste. 5. AI-driven scientific discoveries. Artificial intelligence is accelerating the rate of scientific progress. AI can process vast amounts of data, simulate complex physical interactions, and uncover patterns that would take humans centuries to analyze. Future AI-driven research might help uncover new energy principles that we haven't even imagined yet. The future of energy, not perpetual, but limitless. While perpetual motion machines may never exist, future discoveries could still provide energy sources so abundant and efficient that they feel limitless. By pushing the boundaries of physics, scientists may one day uncover new principles that challenge our assumptions, just as Einstein's theories redefined Newtonian physics. In the next section, we'll explore the greatest mysteries about energy and the universe that remain unsolved, and what they could mean for the future of science. Section 3. The mystery of energy and the universe. Energy is one of the most fundamental aspects of the universe, yet many of its mysteries remain unsolved. While we understand the basic principles of energy conservation and thermodynamics, deeper questions about its true nature continue to challenge scientists. Could these mysteries one day lead to breakthroughs beyond our imagination? 1. What exactly is energy? We define energy as the capacity to do work. But at a fundamental level, what is energy made of? Is it a tangible entity, or is it simply a mathematical concept describing interactions between matter and forces? While we can measure and manipulate energy, we still don't fully understand its essence. Some theories suggest that energy is deeply connected to the fabric of space-time itself. If this is true, there may be ways to interact with energy that go beyond our current understanding. 2. Can energy be created or destroyed? The first law of thermodynamics states that energy cannot be created or destroyed, only converted between different forms. However, some extreme scenarios challenge this idea. For example, the Big Bang supposedly created all the energy in the universe from nothing. How is this possible? Quantum physics suggests that particles can momentarily appear and disappear due to energy fluctuations. Could similar mechanisms be harnessed on a larger scale? Hawking radiation shows that black holes can slowly lose energy and evaporate. Could this process reveal new insights into how energy behaves in extreme conditions? 3. The dark energy puzzle. Dark energy makes up nearly 70% of the universe, yet we have no idea what it actually is. It is responsible for the accelerating expansion of the cosmos, but its origin and properties remain unknown. If we could unlock its secrets, it might lead to new ways of manipulating energy, perhaps even tapping into a previously unknown cosmic force. 4. Could there be unknown forms of energy? So far, we recognize kinetic, thermal, chemical, nuclear, and electromagnetic energy. But could other types of energy exist? Torsion fields and vacuum energy are theoretical concepts that suggest undiscovered ways to extract and use energy. Extra dimensions in string theory could contain hidden energy reservoirs beyond our observable universe. Exotic matter and negative energy might enable technologies like warp drives and stable wormholes, defying our current limitations. The future, a universe full of possibilities. While perpetual motion remains impossible under our current understanding, the mysteries surrounding energy suggest that science is far from finished. The deeper we explore, the more likely we are to find unexpected breakthroughs. Perhaps the next great scientific revolution will come not from breaking the laws of physics, but from discovering aspects of energy that we never knew existed. If you found this video helpful or interesting, please give it a thumbs up and subscribe to the channel.